working here? Yeah. It's all good. Thank you very much. Hope you're all having a great time. I'm sure you're all starting to get hungry as well. All right, so I'm not going to talk about robotics, so take that as you will. Hopefully you'll enjoy it. Anyway, so the problem that we are trying to solve with this work is usually in evolutionary computation, you have representations, and the idea is that your representation is used to express a high diversity of individuals that have different behaviors, but also exhibit high quality, right? So, it's very rare that you optimize a representation to be searchable. Representations are designed and you hope are easily searchable by some evolutionary algorithm. And so this means that a lot of the responsibility on having these representations be searchable is that they need to be handcrafted by the researcher. And the reason why we would want representations that are easily searchable is that we want to be able to elaborate and aggregate complexity over these representations as we evolve our different systems, whatever they may be. So in this work, we were going to try to see if we can make some progress in this direction. So we're going to show that it is possible to learn a representation that is easily searchable by a evolutionary algorithm, whether it be a genetic algorithm or a CMA or whatever it is you want to use. And we'll show that indeed this meta-learned representation can generate diverse solutions that are also high quality. Okay. So how are we going to do this? Generally, these systems have two parts, or our system has two parts. One is a DNA-like representation. So that means a string that encodes some information about what your design process or your developmental process should unfold, or how it should unfold. And a developmental model that decodes this representation into some phenotype space that you would like to explore. The issue here now is that you have two systems. You have the representation you want to search over, but you also have the thing that the system that must decode it. So we need to train both at the same time. So we're going to propose a meta-learning approach to solve this problem. And the long-term goal is that we would like this dual system to be evolvable. We're going to try to see how successful we are in this. Okay, so for the developmental system, we are going to use neural automata. The main reason for this is that they're easy to train, not hard to train, and they're flexible. We don't need to put much thought into designing specific update rules and whatnot, and it could generate a much more diverse set of patterns than standard serial automata, where we need to think about the exact rules of update that we're going to use. So how does a neural automata work? This is, I'm sure all of you know most of this, but we have a set of neurons that have some hidden state. And at each time step, they take input from the neighbors, they update, and they produce some output. We're going to augment this system with an indirect representation, a DNA-like representation, which is global. It's shared amongst all the neurons in the system. And what we want now is that at each time step, we can use this global indirect encoding to guide the developmental process as it unfolds. And how we're going to implement this guidance is using attention. So why attention? Well, because it's all you need, and that's it. A more, I guess, more or less cynical interpretation is that it's easy to train. This is very easy to train. It requires us to also not put too much thought into what exactly this update function looks like, and then just allow it to learn and discover what is useful for what it wants to achieve. And as a first approximation, it's a good step. Okay, so after at each time step, not only will you update the internal state of each cell, but you would also use that internal state to attend to your DNA. You get some decoded vector C, and you use that to condition how your developmental function will unfold over time. And because this is global, it means that ideally the system would learn to use different encodings to generate different things with one unified, one neural automata can generate a diverse set of things using these encodings, which is different from some related work that instead uses one cellular automata per entity that you want to generate. Okay, so how do we train it? Well, we need to introduce this meta training loop. So let's say you first define, we're going to use quality diversity. Why? Because it allows us to both explore the quality and the diversity of the solutions generated. We need to generally define our behavioral spaces. And then in a loop, we assume we have a developmental system with some fixed parameters, and it explores this space. You use some genetic algorithm to generate different DNA combinations via mutation and crossover, and you fill out your repertoire. And you see where your solutions fall in. Once you have this, you run this inner training loop, you can evaluate and say, well, how good was my developmental system, my neural cellular automaton in this case, at generating quality and diversity? And once you measure that, you can use it to update the parameters of your developmental system. So you have a population now of developmentals S, and you apply them to each DNA. In your inner loop, you generate different phenotypes, and you evaluate it. Okay. So that's a setup. How are we going to test this? Well, we are going to take this very simple task. It's generate mazes. So you have traversable tiles and untraversable tiles, and you want to generate solutions that are connected, because you want to be able to traverse to every single point in your maze. So this is our quality measure, and descriptors. This is based on work by Julian Tsakalis's lab in New York, and they use this descriptors that are maximum minimum path length between any pair of tiles in your level, and the symmetry of set levels. So we're going to train the model on this, and we'll see how well it performs. Okay, so this is not working as expected for some reason. Sorry. All right, so we start an inner loop, and it has some set of solutions, and now the model, you use a genetic algorithm, you recombine, generate new solutions, apply the developmental step, and you see, well, why is it not? You see how it just slowly fills up your behavioral space, and this tells you how good it was at discovering diverse solutions. And we can see that indeed these solutions are diverse. So, for example, this is one example, NCA, and it generates. You can see the levels that it is generating, and to what it is attending in that space, as it to which part of DNA it is attending as it generates. And it does indeed find some different patterns. So it does generate diversity. The patterns are still somewhat similar amongst them. So you can say that there's some elaboration, there's repetition and elaboration. It takes a basis, some basic template, and at one point it starts diverging from where it's diverges into different entities, and you can generate diverse phenotypes with it in the face of diverse DNAs. Okay. Now, I guess one important step in this whole research is we need to evaluate different alternatives. So what happens, for example, if we change the DNA genotype for a continuous vector? That would be the simplest possible encoding. And so the trained model that you just saw would be the purple line up here. And you can see that if you use a continuous embedding, so these would be the green and red, they tend to converge quicker. It's easier for the CMAA or the genetic algorithm to find good solutions in that space, but it is it doesn't achieve as good of a performance. It converges to a lower, it achieves better performance overall. However, there are also other, and the model exhibits also other interesting properties. It's not just trainable with a genetic algorithm in the inner loop. You can use CMAA, and it works just as well. So We have achieved somewhat that goal of having it be easily searchable by a genetic algorithm without having to rely on a specific genetic algorithm or a specific evolutionary algorithm, sorry, to train it. But other things seem to also be important. For example, normalizing the hitting states after the updates seems to be help the model a lot to find good solutions. This is probably because the NCA diverges too much if we don't do it. So finally, we get to the original question is, can we make it evolvable? So in here you can see what happens in different generations of the outer loop. So that's different colored curves. And what happens during the inner loop for each of the models at that step of learning. And you can see that the model tends to do something interesting, which is the mean fitness of the discovered solutions that it finds is high from the beginning. So it tends to find really good solutions. And then the strategy it uses to be more evolvable, or to be search the space better, is to elaborate on those solutions. And you can see it because from early generations, performance is already high during the inner loop, but coverage is what then starts to dominate. As training progresses, it covers more and more, and it learns to cover more and more of that descriptor space. Okay, so conclusions. We have shown that we can train a model to be weakly evolvable. And when I say weakly evolvable, is because while it can do, it can cover the space, it does find. It starts with, it first finds a high quality solution and elaborates on them, but, using a DNA-like representation is better for this than using a continuous vector. But unfortunately, it doesn't manage to generalize too well. So it cannot cover a space that's far outside of the space that it learned to cover during training. And that's one limitation that we need to address. So it still hasn't found it still hasn't managed to elaborate extensively on the solutions that it has found. That's future work. And that's it. I would like to thank my collaborators, Eleni, Joachim, and Erwin, PI Sebastian, and thank you for listening.